In the previous video, I showed you via some hand calculation examples why having only this type of constraint is not enough. If we only model that a fish processing factory should ship everything it produces, in addition to the positive value constraint for the decision variable, then we might create situations where our solution, that is the values of the decision variables, are not fulfilling what we want. We can guarantee with these constraints that every factory ships exactly what it produces, but we cannot guarantee, as I showed you, that every customer receives exactly what the customer demands. Therefore, we need another set of constraints. We have to model that a deep freeze warehouse, our customer, should be supplied with everything it demands. Everything means we do not want to supply less than the demand, but we also do not want to supply more than the demand. So now the first line of this set of constraints reflects everything that is delivered to customer A, which is Lulu. So from factory 1 to A, from factory 2 to A, from factory 3 to A, and this should be, the sum of these three should be exactly 81, which is the demand of the Lulu warehouse. Accordingly, we model the same for the shipments into warehouse B, and we model it for the shipments into warehouse C, and we also model it for the shipments into warehouse number D. Only when we have all these three types of constraints together, we do not create an over or under supply of fish cases to the warehouses. We do not supply more than a factory can produce, and of course we only deal with reasonable numbers for the cases. Only when we have these three types of constraints together, the model is doing what we want it to do. Now let's look at the solution of this model. What is a solution to this type of model? This is an optimization model, more precise a combinatorial optimization model, and generally speaking we say that we have a solution to this type of model if we assign a value to all the decision variables. Now, assigning just a value to the decision variables is very easy. You don't need to do any specific calculations. What is more interesting for us is that we are interested in a feasible solution. And a feasible solution is an assignment of values to the decision variables that meets all our restrictions. All the constraints that we modeled on the previous slide are fulfilled. No constraint is violated. If an assignment of values to the variable violates at least one of the constraints, then we say this solution is infeasible. Though there are many solutions that fulfill these restrictions, these constraints, however, we have an objective function to measure the consequences of a solution, and now we are interested in an optimal solution. In this case, optimum means a solution that has minimum costs, and a solution that has minimum costs is a feasible solution, and there's no other feasible solution with lower costs. So we are looking for a feasible solution that at the same time has the smallest cost possible. We are not able to find another solution that has lower cost than our solution. Then we have identified the minimum cost solution. And this is a very interesting and relevant concept. Many companies, of course, often in practice, we do not have these idealized situations. However, we often have many important characteristics of these idealized situations. And when we are able to isolate these characteristics, we can do a lot in terms of supporting the planning and logistics in transportation via mathematical models. Therefore, it's really important to develop the ability to see these, identify these characteristics of the situations. At the moment, I'm supervising 13 students that write their bachelor thesis, and they are going to graduate this year, hopefully. Though they talk to companies, and often the companies tell them, we don't have any real problems. And when I look at the problems, or when my students look at the problems, often we see, okay, the companies are talking about this situation. They have a setup that fulfills all their constraints, all their restrictions, but in most of the cases they did not identify a feasible solution with minimum cost. And therefore they just think they identified, they don't have any problems, but their problem is not of fulfilling these restrictions, these constraints. Their problem is to find a better solution that fulfills all these restrictions for lower costs. This is a very important distinction for practical cases. Let me also tell you that often when we are just talking and when we are not so careful about the terminology, often we assume when we are talking about a solution, we implicitly often assume that it's a feasible solution. This might not be always justified, but when I'm just talking to you about solutions, often I imply a feasible solution. Okay, let's have a look at the complete model. When I perform all the steps from the previous slides and I write it down on one single slide. Here I have my objective function. The objective function is written on the top of the model. In front of the objective function I write min or max depending on the situation. Here I am interested in the minimum cost solution, therefore I write min. Then I write something like subject to the following constraints, sometimes just ST, short for subject to, and then I list all the relevant constraints. The first 3 lines, the first 3 equations guarantee that in each factory we ship everything that is produced. In the lines 4 to 7, I guarantee that my customers receive exactly what they demand. And finally, I tell the model that I'm only interested in values of our decision variables that are 0 or positive. Negative values are not allowed. And then this in total describes the full situation. Now when we have such a model, it is important that all the constraints have to be fulfilled in the same time. Yeah? If only one constraint is not fulfilled, my solution is infeasible. And when the following constraints that I have highlighted here are fulfilled, then I have a feasible solution. Then I calculate the cost of this feasible solution, and this gives me the total cost, the total transportation cost of this problem. Now I am interested in that solution which gives me the minimum total transportation costs. Okay, And this is a way how we can model the situation of our case Selma fishery, and we can decide which factory should provide which number of fish cases to which warehouse of our customers. Now the next question, and a problem that follows this structure is called the transportation problem. So again, let me repeat what I told you in the beginning of this lecture. When I speak of the transportation problem, I'm talking about a problem that follows basically this structure. We have a set of suppliers on the left side, we have a set of customers on the right side, and everything that is available on the left side needs to be shipped to everything that is on the right side. And we are interested in that shipment that reduces the total transportation cost. This structure is called the transportation problem. And the task of the transportation problem is to transport homogeneous items from a set of origins, supply nodes, to a set of destination, demand nodes at minimum cost. This is a full description of the transportation problem, and the main characteristics of this problem are the following. For each origin and for each destination, the supply and the demand respectively is known. The total demand equals the total supply. Check this for our model. The total number of cases on the supply side equals the total number of fish cases on the demand side. We are able to link each supply node to each demand node, and on each link the unit transportation cost is known. These are the assumptions and characteristics of our transportation problem. Now here's a small exercise that should increase your understanding of this problem, your modeling abilities, and your abilities to read the formal description in terms of decision variables. We are given a solution here, and now your first task is to show that this solution that is given here is infeasible given this input data. The next task is you should show, by changing some of these decision variables, how to create a feasible solution. And in item number 2, you should calculate the cost of your proposed solution. And I want you to comment if this solution that you found is the minimum cost solution. Good luck with that.